Hello friends, in today's class we'll discuss the model on which lexical analysis is based on, that is finite state machine. We'll also see few simple pattern. So here the model which that language or token recognizer is based on is basically a deterministic finite automata. Okay, so here we are going to discuss the DFA part. So the mathematical definition of a DFA says that it consists of 5 tuples. Okay, so there is a state Q, sigma, Q0, uh, delta, transition function, and set of final state. Okay, so DFA defined by the 5 tuples, and here Q is the set of state. We know this term that this is nothing but alphabet. Q0 is the start symbol, and the delta is our transition function. F is the set of final state. Okay, so now among this, the most important one is your transition function. Okay, now this delta is the transition function, and this transition function is defined as at q cross sigma is mapped to q. Okay, so this is a mapping. So let's start constructing this DFA, and for very simple language. Okay, so let's construct a DFA. Okay, so let's draw the machine let's start with this. Okay, so now this is my alphabet. Sigma is equal to A and B. So let's try to develop a model that is called DFA. Design a DFA that recognizes all the string ends with AB. Okay, so so let's design this machine over here. So now here there are two ways we can design. One is the table part, and another one is your the diagram part. So I'm more keen, designing right now this table, and this is the starting point. That is the start state. Okay, now this is the start state, and there are two input A and B. Okay, so now in the first case, I remember each and every alphabet over here. So the moment A comes, I remember that my last can input here in this case is A. QS on input A is QA. Here, in case of QS, if B comes, so I'll remember this thing in another state, that is QB. Now, what is a QA state is that I'm doing the linear scanning, and in that last term here coming as A. QA, more number of A's are coming. So in that case also, the last scan alphabet remain as A. So this or the state that I'm creating over here is nothing but it's remembering the last term or last alphabet that we are using it. Okay, so QA on input A, QA on input B. Now A followed by B. The last is A, and then the next symbol is coming here is B, and that we want to recognize. So here this will become QAB. Now this and this are two different type of information they contain. This contain that it guarantee that last alphabet is A. This guarantee last is B as well as the second last is A. Look at QB. QB, if A comes, I will go to QA because it contains the last can alphabet as A. QB on input B, so B, double B, triple B. As many B's are there, so there will be only QB. Now come here as QAB, and in QAB, if again A comes, then last scan alphabet will be only A. And in AB, if again B comes, double B, so it will go to the state QB. This is the convention that we put a starting symbol over here and a star over here. Okay, let's draw this diagram. So here QS is the starting point, and on input, the moment A comes, we remember in QA. If B comes, then we remember this thing in QB. More number of A's are coming, let it be here. The moment B comes, we reach to QAB. B, more number of B here. If A comes, back to this. Okay, in this, if B comes, we'll come back to this state here. And if A comes, I'll go back to here again. Okay, so this is how the diagram will look like for a DFA that recognizes all the string ends with AB. Okay, this is the second part of this construction of DFA, and here the question is that they design the DFA over alphabet A and B, accepting all the language that starts with AB. So we have already seen this ends with AB, but now we want to design the DFA that starts with AB. So as I told you that we have a method where we can construct a table or a diagram, but I personally prefer this the table part. So this is the table that we are going to design, and I always start designing with QS with input A and B. Okay, so now I want the first two alphabet to be strictly AB, and then later part can be anything. So QS qualifies, starts with A, the first symbol is A. I will say as QA, but if it starts with B, then we don't want the first alphabet to be B. So for the time being, I'm leaving it as blank. QA, the second alphabet here is also very strict here that it has to be a B. It cannot be a A. So QA on input A, I'm again putting it a blank, and the moment it will come, you satisfy the condition that first alphabet is A and second alphabet is B. Now QAB on input A, now my condition satisfied. After that, anything you want you can write here. So it will be QAB and QAB. Now here the blank that I left here is basically a not allowed case, that it is not allowed to have the first symbol as B. So we are at a special state, and that is called the reject state. So once you are trap state or reject state, you are not coming out of it. So now this is your initial state, and this is the final state. And this is the reject state, trap state. Okay, R is a reject state. And once trap, okay, once goes into reject state, it traps there. That means it will never come out. Okay, so that is the reject state. Or why we use it? Why we use a reject state? The only thing that we use the reject state is for if it is not allowed. Okay, so that only use add a reject state. Okay, add a reject state if it is not allowed. Okay, to add a reject state if it's not allowed. Okay, let's quickly construct this diagram here. So this is your QS, the starting point, and here we are having a state on input A is going to the state QA. Here, if the first alphabet is B, we are rejecting it, and first alphabet is, if there is another A, second alphabet is A. If the first alphabet is B, and then it will become QAB, and then there will be A or B. Okay, so now this is the diagram, and this is the reject state, and that loops on A and B. Okay, so this is the deterministic finite automata that is accepting all the string over A and B that starts with AB. Okay, this is the next part, and in this we are constructing a DFA which accept all string with substring AB, and of course this alphabet is of course here in this case is A and B only. Okay, so we want to accept all the string with the substring AB, and we will design the DFA for this, and this DFA will, okay, so this is a QS start state, and your input alphabet is A and B. So now substring AB means AB is essential. Okay, so now here when we say substring AB is AB. Okay, AB must be present. Now the question is where it will be present. So that really does not matter. That as long as AB is present, so AB can be present like here. A is a valid string. B is a valid string, and if I say A is a valid string, so somewhere definitely this AB will always be there in the picture. So AB is present, AB is present, and AB is present. So must AB is must, it must be present over here regardless of the position. So QS, I'm looking for AB, and the moment the first A will come, I will say that yes, there is a single A present, so QA. Now B, I will not reject it because it is not the restriction. Okay, like previous question, there was a restriction on position number, but here there is no restriction. So QS on input B, I'll remember here in this case, and now here, unlike the previous situation, I'm remembering in QS. Previous situation means the first problem that we have discussed. Okay, so there I created a separate state, and here I'll just put it in QS only. I'll tell you the reason for that. QA, more inputs are there, so QA will remain in QA. Okay, it will remain into QA, and on input to B, it will become QAB, and my condition is fulfilled. In QAB, now here we are looking for the substring part, and the substring part, the moment AB will occur, okay, somewhere, we don't know where, but somewhere if AB occurs, anything comes will be acceptable. Okay, so after that AB, what is coming after that is really does not matter. Okay, so we are not bothered or concerned with this part. So now with that, I'll say QAB and QAB. So this is my starting point, and this is my final state. Okay, so that is the diagram for this. So now this is a state QS. Okay, now here I could have created a state for like in the first problem I have given here as QB. I could have done here also, but you understand that the behavior of, suppose, okay, let's take that also. If I create a separate state QB instead of QS, this is a behavior of QB would have been, okay, QB. So I'm looking for A. The moment A will come, then it will become QA. And the moment B will come, it will loop. Okay, so this is the state that would have been created if I have a QS. But now you understand that this QB is having the same behavior as QS. QS is also on input going to QA, and this is also QA, and this is QB if it has been there, and this is also QB. So the behavior is same, and that is the one of the way we minimize our requirement or DFA. Okay, let's come back to this diagram, and here QA on input A is going to the state QA, and then B it is looping, and then A and B going to the state Q A B. More number of A's are there, then it will loop. And then this is the final state, and on input A comma B, and it's just making this. Okay, so now this is the machine and this is the table. This is the transition diagram that accepts, okay, that recognize linearly. Okay, I'll do the linear scan. You give me a string which is consist of, let's say, triple A and then B, and then I'll say AB. So linearly I can scan, I can say that this is A, so I'll be here, another A I'll be here, third A I'll be here. The moment B will come, I'll reach to the final state, then again A and B will be coming, and then I'll be, so linear scanning. Okay, linearly I can scan, and linear scanning, and I can say that whether this one is following this particular rule or not. Okay. So now we have seen few example of the DFA, and so this is the model which this token generator are based on. So we have, for each token we have to design what? We have to design the DFA for this.